Hi, in this video, let's look at what is simple harmonic motion, in short SHM. Let's look at this system here, where from a firm ceiling, a spring is attached and a mass of, let's say, an object, a sphere of mass m is attached to the spring. Now, this system is at rest. It's not moving up or down. And let's say that this is at rest. We can call this the equilibrium position, and it's at rest. Now let's say I pull this mass down and then leave it. I just pull this mass down and leave the system. What would happen? You would see that when I pull this mass down, the spring gets stretched downwards, and then when I leave it, it goes back up, crosses the equilibrium position, and goes beyond the equilibrium position upwards. Then again it starts coming downwards, crosses the equilibrium position, comes to this point, and then goes back up to this point. So it keeps moving up and down. It repeats the same motion periodically. Now this repetition of the same motion periodically in cycles is called simple harmonic motion. Right. Let's look at what happens to the forces, the acceleration, the velocity of this object, of the system in these various positions. One is the equilibrium position, right? Let's take this as position one extreme, the mass reaches. Then when it goes back up, it crosses the equilibrium position and goes to this extreme position. Let's mark them as positions 1 and 2. Now in the equilibrium position, let's look at what would be the force. The spring is at rest, so the spring force and the mass pulling down the mg, the weight is all balanced out. There is no net force, and hence there is no acceleration or movement of this mass upward or downward. So the spring stays at rest, and there is no force exerted by the spring itself. But here in position 1, the spring is stretched downwards. So when the spring is stretched downwards, it wants to go back to its equilibrium position. It wants to come back here to this position. So it will pull back up on the mass. This is the mass, and it pull back up on the mass. But then when it is stretched and reaches 1, for this system, this is the max position. 1 is the position where it is the stretch to the maximum, and hence the force exerted by the spring or the pullback of the spring will be the maximum here. We know that force is mass times acceleration, and hence the acceleration is going to be maximum at position 1. The same way, when it goes back up to position 2, the spring is compressed maximum for this system. The spring is compressed max, and hence it would want to come back to the equilibrium position again. It would want to come back to and it will push back on the mass to come back to the equilibrium position. So, and since we know this is the maximum compression, the force here also would be the maximum for the compressed state, and we know F is equal to ma, and hence here the acceleration would be maximum. So we can say that the acceleration would be maximum in position 1 and position 2. This is the max acceleration of the system. But what happens in the equilibrium position? In the equilibrium position, when it goes up and down, as it crosses the equilibrium position, the spring is in its comfortable state where it was not exerting any force as in here. So the force is not exerted by the spring in itself. The object, of course, the mass would have a certain velocity. It would have gained due to acceleration, and it would continue to travel further up or down. But the spring in itself, the force is zero, and hence the acceleration would be zero at the equilibrium position. But what happens to the velocity? Let's take the velocities into consideration and study them. Okay, before that, if you observe here that if we take the equilibrium position as zero displacement, the displacement is zero here, then in positions 1 and 2 there is a certain displacement, but when it's in position 1, the acceleration is in the opposite direction. The object, the mass m, would accelerate upward from here, and when it's in position 2, the mass m system would accelerate downward from here. So if we take this as the positive direction of displacement, I mean, if we take the downward direction as positive direction, when the displacement is positive, the acceleration is maximum in the other direction, opposite direction, upward. When it's in position 2, it would start accelerating downward, and hence the compression force is maximum here. The acceleration would be, after this, would be in the downward direction, right? If we take the displacement, the upward direction as the negative direction for this system, then you can see that in both cases, the displacement and acceleration are in the opposite direction to each other. But we know that when it's maximum displaced, the acceleration is maximum, either at position 1 or 2. The displacement is maximum, acceleration is also maximum, but then in the opposite direction. So we can say that acceleration is directly proportional to the negative of the displacement. Now let's look at the velocities. What happened to the velocity? What happens to the velocities in these positions? Here in position 1, we know the object has reached its maximum extreme 1, and hence would change direction and go in the other way. So the velocity we know would be 0 here. The velocity would be 0. And similarly in position 2, the velocity would be 0 because it's going to temporarily stop and then turn to the other direction and come. So velocity would be 0. We see that the acceleration is maximum in position 2, velocity is 0. Acceleration is maximum in position 1, velocity is 0. But in the equilibrium position, the acceleration is 0, but then the velocity would be maximum. Because when the object is at the extreme, either 1 or 2, and then starts accelerating towards the equilibrium position, it keeps gaining velocity till the equilibrium position, at which point the acceleration becomes 0 in the equilibrium position, and hence it stops gaining velocity at the equilibrium position. It has a velocity, but then it stops gaining velocity. That means it has already reached its max velocity at the equilibrium position. We can also look at it this way. If we have a velocity plot of an object versus time and say this is the velocity it goes. At the max position, we know that rate of change of velocity is acceleration. Rate of change of velocity is acceleration. We know that rate of dv by dt is nothing but the slope of this curve for velocity time plot. If the slope at this point is 0, the slope is 0. So when velocity is maximum, acceleration is 0. So it's the same thing that we are telling here, that when the acceleration is 0, the velocity is maximum in the equilibrium position. So at the extremes, the velocity is 0. The equilibrium position, the velocity is maximum. Thank you.